To solve this logarithmic equation, we gotta remember the definition of the logarithm. Plus, there's a four-step process that we need to follow. First, you need to make sure that the expression is condensed. Condensed meaning that there must be only one logarithm on the equation. Okay, so as we can see on the left side, there is only one logarithm, which is called the ln natural logarithm. There's only one. So that means that this is already condensed into one log. So in this case, we're going to go to step 2, which says the following, that we need to rewrite that expression into exponential form. Now, the definition says the following. The definition says that log base b of x equals to y is equivalent to b to the y power equals to x. Okay. So the only thing that we are missing in this logarithm is the base. But anytime we have a natural logarithm, by definition, the base is automatically the number e. So that is the base in this logarithm. So your x is represented by the square root of x plus 9, and the exponent y that you see on that expression is 2. So if we rewrite it in exponential form, it would be e to the power of the second power, e to the power of 2 equals, which is b to the y power, that's what you see here on the right side, equals to x, but in this case x is represented by the square root of x plus 9. Then what we need to do is step number 3 tells you, step number 3 tells you to solve for x. Now to solve for x in this one, since there is a square root, we cannot take out the 9 out of there yet because it is inside of the square root. So the first thing to get rid of that square root is to do the opposite of square root, which is raising it to the second power, but we have to do it to both sides of the equation. So we already know the square root and the square will cancel each other. And then e square square, when you have a power raised to a power, remember the rule says that you multiply them. So that's e to the 4th power equals to x plus 9. And then to leave the x by itself, we need to subtract the 9 from both sides. So my answer for this is x equals to e to the 4th power minus 9. Okay? And of course, to complete this problem, you type this answer into the calculator. Let me go ahead and do that. So we put e to the 4th power minus 9. The answer should be in your calculators 45.59815003. So we round it to, it says right here, 2 decimal places. So the answer in 2 decimal places is 45.60. Okay. So that is the value of x. Alright. So what we need to check, again, check the domain. Now, in order for you to check that solution, you need to check the domain. Okay, so the domain of this expression, you have to say the domain, you always find it by setting the expression right next to the logarithm greater than 0. So x plus 9 must be greater than 0. Okay, so in this case, if I solve for x, I subtract the 9. So the domain of this logarithm says that x must be greater than negative 9. So all I have to do is I need to make sure that the domain is in this answer that we found is in the domain. So that is my x. So 45.60. Is that answer greater than negative 9? Yes, right? So since that answer is greater than negative 9, that means it is a solution. So 45.60 is a real solution. Okay? Now, next question. We're going to solve the following logarithmic equation. So we're going to follow the same procedure. In this problem, the very first thing that we must do is that we need to condense that expression, because as you can see, this expression contains not one but 2 logarithms. Right? There's 2 logarithms in this expression. So there is a formula that tells you that anytime you have the log base b of m plus the log base b of n, that is equal to the log base b of m times n. This is the product rule. So I'm going to combine these two logs using that formula. So the log base 6 of x, right here my m is x, right, plus the log base 6 of n is this expression right here, which is 5x minus 1, equals, I'm going to put it here, log base b, which in this case is 6, of m, which is x, times n, which is 5x minus 1. And of course I'm going to put the number on the other side, which is equal to 1. That was the first part of the process. Step number 2. Now we need to rewrite this expression using the definition of the logarithm. So we need to write it in exponential form using the definition. So write it in exponential form. So definition. The definition again says that the log base b of x equals to y. That is equivalent to b to the y power equals to x. So right here what we can see is that the base is 6, right? My x is represented with x times 5x minus 1, and my y is 1. So b, which is 6, raised to the power of y, which is 1, equals to x. In this case, my x is represented by x times 5x minus 1. Next thing we must do, we need to solve for x. So let's first of all raise the 6 to the first power. 6 to the first power is 6, equals to x times 5x minus 1. Then we need to distribute right here, so we need to undo any parentheses. Distribute that, so that gives you 5x squared minus 1x equals to 6. Now, since this is a quadratic equation, quadratic means to the second power, that means that we need to try to factor this expression or use the quadratic formula or the square root property to be able to solve this. So the first method that we need to think about is factoring. Now, in order for me to factor this, first of all, keep in mind that you need to equal one side of the equation to 0. So I need to subtract the 6 from both sides of this equation. So that gives me 0 equals 5x squared minus 1x minus 6. And then we're going to factor the trinomial. This is a trinomial, and the trinomial we factor it by multiplying the a times the c, which is 5 times 6 is 30. Then we need to find two numbers that multiply to 30 and at the same time they subtract to this number right here, which is 1. So it would be 5 times 6 subtract to 30. Right? I mean, multiply to 30 and subtract to 1. Those are the factors we need. So we open two parentheses. We put x and x on each parenthesis. Then the factors, which is 5 and 6. Then since this is a negative 1, remember that the biggest of these numbers carries this sign right here, so it's going to be negative 6 and positive 5. Okay. Last step of this factoring process is when after you put the factors, is you need to keep in mind that you need to divide by a. In this case, a is 5, so I'm going to divide both of them by 5 right here. And that is going to give me x plus 1 in the first parenthesis, 5 divided by 5. And the second one, since you cannot divide by 5, then you're going to bring the 5 in front of the x. Since you cannot simplify this fraction, so automatically this becomes 5x minus 6. And then we equal each one to 0. And we find the solutions for x. X plus 1 equals to 0. 5x minus 6 equals to 0. So if I solve for x right here, minus 1 on both sides, that gives me x equals negative 1. And right here I move the 6 over, so that gives me 5x equals to positive 6. Then if I divide it by 5, x equals to 6/5, which is equal to 1.2. Okay? Those are my two solutions. But now keep in mind that we need to check the solutions. I'm going to do the checking right here. To check them, we need to first find the domains of the original logarithmic expressions by setting them greater than 0, each one. So we're going to go all the way to the originals to the top, and we're going to say that this x must be greater than 0, and that is already x by itself, so that is my domain of the first one. Second, this one says that 5x minus 1 must be greater than 0, so if I solve for x, I move the 1 over, so you get 5x is greater than 1, and then I divide it by 5, so x must be greater than 1/5. These are the two domains that the answers must satisfy in order for them to be real solutions. So let's go ahead and prove it and test it. So we know that the domains x must be greater than 0 and x must be greater than 1/5. So we're going to start with the first answer, -1. I'm going to test this answer right here. Hold on. I'm going to test that answer on the side right here. -1, is that greater than 0? That is completely false. Right? And if we check it right here, -1, is that greater than 1/5? That is also completely false. So that means that -1 is not a real solution because it's not in the domain. Now, we're going to check the second solution, which is 6/5. Okay? X, which is 6/5, is that greater than 0? That is my first domain, and that is true. X, which is 6/5, is that greater than 1/5? That is also true, so that means that 6/5 is the only real solution, in fact. Okay? Next equation. On this one, we're going to do exactly the same thing as we did on the previous one. To solve for x, what we need to first do is that we need to condense the logarithmic equation, which is write it into one logarithm. Okay? And right here we see one special property. The special property for condensing says that log base b of m minus log base b of n is equivalent to log base b of m divided by n. This is called the quotient rule. That's exactly what we need to do to condense this left side of the equation. You see that m right here is represented by x plus 19, and n is represented by x minus 5, and the base is 5, right? So my expression, if we put it back together into one log, it would be the log base b, which in this case the base b is going to be base 5, of m, which is x plus 19, divided by n, which is x minus 5, and of course we need to write the other side, which is equal to 2. This is my new equation. Okay? Then what do we need to do? Step number 2. We need to use the definition of the logarithm to rewrite this equation in the exponential form. Remember, the definition says that log base b of x equals to y is equivalent to b to the y power equals to x. Right here my b is 5, my x is represented by this fraction, and my y is 2. So b, which is 5, we're going to write it here, to the power of y, which is 2, equals to x, which is this fraction, x plus 19, divided by x minus 5. Now, step 3, solve for x. First of all, we need to raise this number to the second power, which is going to give me a 25, equals to x plus 19 divided by x minus 5. Then, when you're solving an equation that has a fraction, first thing that we need to do, we need to clear the fraction. To clear that fraction, we multiply both sides of this equation by the denominator, by the least common denominator, which in this case is x minus 5. We multiply the x minus 5 on the left and on the right. So on the right side, of course, the purpose of multiplying it is so that we can get rid of that fraction, so it cancels. On the left side, so we're going to end up with x minus 5 times 25 equals to x plus 19. What do we do next to solve for x? we distribute the 25 on the left side to x and negative 5, right? 25 times x is 25x, minus 25 times 5 is 125, equals to x plus 19. There is no need for us to factor in this equation, because there is only x to the first power, so all we gotta do is combine the x's to the same side, leave the x by itself, and that will solve my x. So we're gonna subtract this x to the other side, so that gives us 24x minus 125 equals to 19. Then we add the 125 to the other side, so we get next 24x equals, this cancels, 125 plus 19, 144. Okay, and then we divide both sides by 24 to leave the x by itself, and make sure that when you get this answer right here, you if you cannot divide, you leave it as a fraction. If you can divide, then of course you divide. And 24 goes into 144 6 times exactly. So 144 divided by 24 equals to 6. So the answer for this equation is x equals to 6. Can I say that that is a real solution automatically? No. We have to check the solution. How do we check it? By looking at the domain. So we're going to go back all the way to the top, the original logarithmic expressions, and we're going to say, right here, x plus 19 must be greater than 0. So if I subtract the 19 to leave the x by itself, the domain tells me that x must be greater than negative 19. That is the first domain. Second one, x minus 5 must be greater than 0. So if I move the 5 over, I add it. And the domain of the second one tells me that x must be greater than 0 plus 5, which is positive 5. These are the two domains for the two original logarithmic expressions. That x must be greater than 19, negative 19, and x must be greater than 5. Let's check the domain and see if it is true. X must be greater than negative 19, and x must be greater than 5. So if I substitute this answer into the x, is it true or false? Is 6 greater than negative 19 true? Yes. Is 6 greater than 5 true? Yes. So that means that x equals to 6 is a real solution. The next logarithmic equation. On this one, we are going to do the same thing. Solve the logarithmic equation. Be sure to reject any value of x that is not in the domain of the original logarithmic expressions. Give the exact answer. Okay. So right here, we're going to do the same thing. But on this one, we're going to apply two rules. Okay. First of all, I'm going to start off with condensing, right? So I'm going to condense the first two logs, these two. And then I'm going to work with the third one. Okay. So first thing, these two logs, if you see them, they look like this: log base b of m plus log base b of n, and according to the definition, that is equivalent to log base b of m times n. So I'm going to condense these two logs, and they will become, this is my b, of course, and my m is represented by x minus 8, my b, which is 7 again, and my n is represented by x minus 2. So log base b of m, which is x minus 8, plus log base b, which is 7, of n, which is x minus 2, equals log base b, which in this case, I forgot, my base b is base 7, of m, which is x minus 8, times n, which is x minus 2. Okay? And now I'm just going to bring down the rest of the information. And then you see that the rest, we now have this, right? So I'm going to bring down the rest. Minus log base 7 of x equals to 1, right? That is the other side that I didn't do yet. Okay? So far so good. Now, what do we need to do next? Now, if you look very carefully, my new expression. Now we still have two logs that we still need to condense. We need to condense these two logs. But now look at what we have. What we have now is this. Log base b of m. Now my m now is going to be all of this right here, minus log base b, which in this case my bases are 7, right, of n, which in this case my n is x. When you subtract, the rule tells you that you are going to change it to division, combine it into one log under division. Log base b of m minus log base b of n equals to log base b of m divided by n. So we're going to combine it into log base 7 of m, which is x minus 8 times x minus 2, that is my m, x minus 2, divided by n, which in this case n is x. And of course I'm going to write the other side, equals to 1. So I'm just going to bring the 1. Okay. Next, now that we have condensed it into one log, we're going to use the definition of the logarithm again to rewrite this equation in exponential form. The definition of the logarithm says that log base b of x equals to y is the same as b to the y power equals to x. And if we take very close attention, the base b is 7, my x is represented by this fraction right here, and my y, it is 1, right? So b, which is going to be 7 raised to the y power, which is 1, equals to x, which is this fraction, x minus 8 times x minus 2 divided by x. Step 3, now we need to solve for x. First we need to raise that 7 to the first power, which in this case 7 to the first power equals to just 7, equals to x minus 8 times x minus 2 divided by x. So we end up with another case here in which we need to get rid of the fraction. And remember, to clear the fraction, first thing we need to do is multiply that denominator on both sides of the equation, my least common denominator. And again, the x's on the right side cancel out, so you end up with x times 7, which is 7x, equals to x minus 8 times x minus 2. Then we need to FOIL, right? So that's the next thing we do. We're going to multiply x times x, which is x squared, x times negative 2, which is negative 2x. Then we multiply negative 8 times x, which is negative 8x, negative 8 times negative 2, which is positive 16, and that equals to 7x. Then we can combine like terms. So we end up with 7x equals to x squared, negative 2x minus 8x is negative 10x plus 16. That is a trinomial again. Remember that before we can try to either factor or use a quadratic formula to find the solutions, we need to equal the other side to a 0, so we need to subtract the 7x, but we need to put it with the 10x, right, because those are the like terms in this equation. So that gives me 0 equals x squared, negative 10x minus 7x is negative 17x plus 16. Now in this case you see that the value of a is 1, right? There is no number in front of the x squared, so we just need to find the factors of the last number, right? Because there is no a value. So we just find the factors of 16, the factors that multiply to 16, and according to this sign tells me that when I add them they give me 17, so the factors will be 16 times 1. So we open two parentheses, and we don't need to worry about the value of a because it is a 1. All we got to do, put the factors in the right place, 16 and 1, and put the signs in the right place. Since it has to add up to a negative 17, then both of them must be negative. Negative 16 plus negative 1 equals negative 17. Right? Then we equal them to 0. So x minus 16 equals to 0. And right here, x minus 1 equals to 0. So I add the 1 to the other side here. So it gives me x equals to 1. I add the 16 right here to the other side. So x equals to 16. Can we automatically say that the solutions are real? No. What we need to do, we need to check the domain to see if both of them are in the domain. That's how we check if they are real solutions. Okay. So we are going to go back to the original logarithmic expressions, and we're going to find the domain. Okay. The first one, x minus 8 must be greater than 0. So if I solve for x, x must be greater than positive 8. Same here. X minus 2 must be greater than 0. So if I add the 2 to the other side, x must be greater than 2. And the last one that has only x by itself, x must be greater than 0, and that is already x by itself. So these are the three domains for each log. X must be greater than 8, x must be greater than 0, and x must be greater than 2. Okay. So let's go ahead and put them here. X must be greater than 8, x must be greater than 2, and x must be greater than 0. And we're going to check if both of these solutions are in the domain. So I'm going to start with, let's say, 16. I'm going to start checking the 16 first. So I'm going to put an arrow here, and I'm going to check the 16 right over here. 16, is that greater than 8? That's true. 16, is that greater than 2? That is true. And is 16 greater than 0? That is true. So what does that mean? That 16 is a real solution. Do the same with 1. X, which is 1, is that greater than 8? That is automatically false. And if you check the other ones, 1 is greater than 2, that is automatically false. The only one that is satisfied is the last log, but in order for it to be a real solution, it has to be true on all the domains. It is false on the first two, even though it is true on the last one. It is not a real solution because it is not in the domain of all the expressions. So the only real solution for these equations will be x equals to 16. Alright, next equation. Now for the next one, it is going to be a little bit different. This is the last one that we're going to work on, and we can approach this question in two different ways that I will show you. We're going to do it with the regular definition. It can still be done the same way that we did it previously, but it can also be done in a different way, okay, an easier way than that. I'm going to show you both. Now, for this equation, the first thing is that we need to make sure that we can put all the logs on one side of the equation. That is one way of doing it. Okay, so I can either bring these two logs over to the left side or bring this log over to the right side, whichever way you want to do it. It is okay. It is going to give us the same result. Let's say we bring this log over to the right side. So I just need to subtract it over so that we can bring it over to the other side. So I subtract it over right here. Okay, so that's going to give me a 0 on the left side equals log of x plus log of 11 minus log of x plus 11. Okay, there are three logs that we need to condense. So let's start off by condensing the first two. The formula for the first two, you should already know it. It tells me that if I have an expression in which I have log base b of m plus log base b of n equals log base b of m times n. This is the definition that we can use for these two logs, right? That's what we can do. So we're going to begin with that one. So we see that the b, we don't see the b right here, but automatically keep in mind that when there is no base, that means that there is a 10 right here on this base as the log. But we don't see it because that is the default base when there's no base. The things that we need to see here is that the m is my x and my n is my 11. So if I want to condense them, log base b of m, which is x, plus log base b of n, which is 11, equals to log base b, which in this case is log base 10, we don't have to put the base 10, of m, which is x, times n, which is 11. Then I'm going to write everything else. Okay. I'm going to rewrite that because log base b of x times 11 is the same thing as log of x times 11 is the same as log of 11x. Right? I'm just going to rewrite it. Then, the next thing that we would do is that we can condense it again by doing the second rule. The second rule right here, I'm going to highlight it so that you don't get it, you don't mix it up here with the rest of the stuff. This is the formula. The formula tells me that if I see log base b of m minus log base b of n, that is equal to log base b of m divided by n. This is my next formula, right, which is called the quotient rule. That's what we need to apply right here. What we can see on these two logs is that the m is my 11x, right, and my n is my x plus 11. So if we put them together into one log, it will be log base b, which we don't have to put the base because it's 10, of m, which is 11x, divided by n, which is x plus 11. And then we write everything else equals to 0. Then what else? We need to, now that we have to condense that into one log, what do? We need to use the definition of the logarithm, and we need to rewrite this in exponential form. So right here you see that the y is on the left side, right? Y equals to log base b of x, that is equivalent to b to the y equals to x. What we see on this log is that the y, my exponent, which is the y, is 0. My base b right here, we don't see it, but automatically when there is no base, automatically the base is 10. And my x in this expression is represented by this fraction. Okay? So, we're going to rewrite it in exponential form, which is b. b is the base, which is 10 in this case, to the y power, y is 0, equals to x, but x is represented by that fraction, which is 11x over x plus 11. And then step number 4 and last, we need to solve for x. Right here we already know that anything to the 0 power automatically equals to 1, equals to 11x over x plus 11 over x plus 11 right here. In order for us to solve for x, just like on the other questions that we have fractions, we have to get rid of the fraction by multiplying that denominator on both sides of the equation. So I multiply the x plus 11 on this side of the equation, and I multiply the x plus 11 on this side of the equation. Okay, and we already know that the x plus 11 on the right side is going to cancel. So if we multiply the 1 times x plus 11, this is going to give us x plus 11, right? Because times 1 is just going to stay the same, equals to 11x. There is no squares, so all we got to do is solve for x. So I'm going to move the x over to the other side to combine it with the other x. So we got 11 equals to 10x, and then to leave the x by itself, we divide by 10. So the answer for this equation is x equals to 11 tenths. You cannot divide 11 by 10, so you leave it in fraction form. Okay, and then you check the domain to see if it is true, and that's how you finish the problem. So let's go ahead and check the domain. I'm going to do a little check on the left side right here, because On the right side, I'm going to show you the second method that you can use. Okay, let's go back to the original logarithms. Okay, right here, to find the domain of this one, we say that x plus 11 must be greater than 0. So if I move the 11 over, x must be greater than negative 11. That is my first domain. And the second one, x must be greater than 0. So that one is already x by itself. So that is my second domain. The third one has an 11, so the third log is not counted as the domain since that one does not have an x. So x must be greater than negative 11 and x must be greater than 0. So we're going to go down here. X must be greater than negative 11 and x must be greater than 0. So we're going to substitute this solution into the x and we're going to check. 11/10, is that greater than negative 11? That is true. 11/10, is that greater than 0? That is true. So that means that 11/10 is what? A real solution. Now, let me show you the second approach to this problem. The second approach, the method number 2, is it only works whenever you have logs on both sides of the equation. Okay? That method number 2 tells you the following. First, you're going to condense the left side of the equation and the right side of the equation, which means that on the left side there must be only one logarithm, and on the left side you can see that there's only one log already. The only thing we need to condense is the right side, and we have already done that here. So I'm just going to write my solution for that. So we condensed it right here, so I'm just going to write it there. Okay, so that is the same as log of x plus log 11 is log of x times 11, which is log of 11x. Right, we did it before. Then the next thing we must do is that there is a little definition. It is called the one-to-one property of logs. And it tells you the following of logarithms. It tells you that if you have the log of some base of m, I'm just gonna say m, okay, equals to the log of some base v, which is the same base on both sides of some n, then you can cancel out the logs right here and set m equals to n. That's another property that you can use here. Whenever, that only works, of course, when you have logs on both sides. So what I can do here, since the log of x plus 11 equals to the log of 11x, and we have the same log on both sides of the equation, one-to-one property tells me that I can cancel out the logs from both sides, and I can set m equals to n, which is x plus 11 equals to 11x. And then we can solve for x. So we move the x over to the other side, so that gives me 11 equals to 10x, and then we divide it by 10, and guess what? We end up with the same answer. Okay? So the answer for this is x equals to 11/10. And we already checked that it is a real solution down here. So it is exactly the same answer as this. Right? And that concludes this section, the end of section 4.4. Have a great day.